The room is almost dark, lit only by a wall of artificial night. Across it, a thin blue web hangs in the air, a lattice of points and threads. Each point is a galaxy. Each thread is a chain of clusters. The web is not an artist's sketch. It is a survey, a measured portrait of the universe taken with telescopes that stare across billions of light years. The people in the control room sit under this digital sky as if they were standing on a balcony outside the cosmos, watching it evolve in a single frozen frame. For most of our history, we thought we knew what that frame was telling us. When astronomers first compared the light from distant exploding stars with the nearer ones, they saw something that did not fit the old script. Faraway galaxies were not just moving, they were racing away faster than the closer ones, in a way that pointed to a strange conclusion. Space itself seemed to be stretching, and the stretching was accelerating. It was as if the universe had found a hidden engine and pushed the throttle forward. To account for that push, we invented a term, a smooth something filling emptiness that urged galaxies apart. On paper, it could be simple. If this outward pressure stayed exactly the same at all times and in all places, then the future was already written. Distances between galaxies would grow without limit. Stars would extinguish one by one, spread thinly through an ever colder, ever quieter void. There would be no sharp ending, only an endless thinning out. A universe that ages not toward a wall but toward a dim, slow fade. Now the web of light on the wall hints that this story might not be quite true. When you zoom in on that cosmic lattice, you are not just looking at pretty structure. You are looking at a fossil of how space has expanded over time. The spacing between certain types of galaxies carries a memory of how quickly the universe grew and how fast that growth changed. When researchers compare those patterns to the predictions of a perfectly steady outward push, they see tiny but persistent mismatches. The map seems to be leaning away from the idea of a push that never changes. The paradox is quiet but profound. The first measurements told us that expansion is speeding up. The newest maps whisper that the thing causing that acceleration might itself be evolving. How can the universe both accelerate and yet drift away from the behavior of a fixed, eternal, repulsive force? What is wrong? The instruments or the story? Think of it like this. You are in a car that has been speeding up for a long time, and all your life you have assumed that the foot on the pedal would never lift. Out the window, the trees and houses begin to blur. Eventually, though, if the driver eases the pressure even slightly, the blur will change. The speed may still be high, but the way the view transforms will not match what you expected from a forever growing push. The instruments on the dashboard see that subtle shift even if your body does not. That is the situation we are in with the cosmos. At the level of everyday life, nothing feels different. The moon still rises on time. The sun still burns as it did for our ancestors. Yet at the scale of billions of light years, the cosmic dash panel is blinking in a way we did not predict. To some teams, the signal hints that the mysterious energy driving expansion could be slowly running out of steam. To others, it suggests that our picture of space itself might be incomplete. From here, two very different futures open up. In one, the invisible field responsible for the cosmic shove behaves like a reservoir that is slowly draining. For a very long time, it dominates, pushing galaxies apart, drawing out the web and thinning the filaments, but it does not last forever. As it ebbs, another ingredient buried in the equations of gravity starts to matter, one that does not push outward, but prefers curvature, confinement, a tendency to pull the great fabric back together. In that scenario, the universe is not on an endless climb. It is tracing an immense arc. Expansion slows, stalls, and eventually reverses over tens of billions of years until, far beyond the age of our sun, the cosmos begins a long, slow fall inward. In the other future, the problem is not a draining reservoir, but a subtle twist. Some researchers explore the idea that the universe may have a tiny global spin, a preferred direction written into its very structure. Inside such a rotating space, the motions of galaxies could mimic the effects of a repulsive energy. What we interpret as a push might be, at least in part, the sensation of living inside a gigantic, extremely slow whirl. If that whirl is not perfectly constant, if its rate changes over time, the apparent cosmic acceleration would also shift. Both stories try to account for the same clues. Both could, in principle, explain why the web on the screen does not align perfectly with the simple, steady push we once believed in, and both carry extraordinary consequences. Is time headed toward a cold, endless hush, or toward a distant epoch where expansion hesitates, fails, and gives way to a gathering storm of gravity? If space itself is turning, what does that do to our assumption that there is no special direction, that the universe has no preferred axis at all? Step outside the control room and onto an ordinary balcony under an ordinary night, and the sky looks indifferent to these questions. The constellations hang where they always do. The Milky Way is a pale band, not a data set. Yet the fate of every star in that band, every planet around those stars, and every mind that may one day wake beneath them, is tied to whichever story is correct. A small change in the behavior of the dark background that fills space could compress the total time available for life and thought from endless to merely very long. We live at a moment when the difference is just beginning to show up in the numbers. Our telescopes are now precise enough to notice that the cosmic train may not be accelerating exactly as expected. Our models are clever enough to imagine fields that thin out and spacetimes that spin. For the first time, we see a fork in the road far ahead. One branch vanishes into a distant gray silence. The other curves down toward a future where the light that is escaping now may someday be drawn back. Which path is our universe truly on, and how will we know for sure? For more evidence-based journeys through time, like and subscribe to the Quiet Universe channel. In the beginning, acceleration looked eternal. The story was clean. When light from distant supernovae arrived weaker than expected, astronomers concluded that the galaxies were not slowing under gravity, but being pushed apart by something unseen. It was the neatest paradox in modern cosmology. A universe whose content was mostly invisible yet somehow controlled its destiny. The numbers seemed consistent, the theory elegant, the phrase dark energy entered textbooks, and the fate of everything appeared sealed. Now the edges of that confidence are starting to fray. The new maps from galaxy surveys like DES and DESI reveal subtle distortions in the cosmic web. These distortions are not random. They suggest that the rate of expansion might not be entirely smooth. Across billions of light years, the rhythm could be changing. The push might not be constant after all. In the control rooms where these maps are drawn, this realization feels like hearing a faint wobble in a perfect metronome. A rhythm once thought steady begins to drag by fractions of a beat. If that beat defines the age and size of the universe, then even a tiny drift could change the finale entirely. The first clue came from statistics that track the distribution of galaxies by scale. Astronomers expect certain patterns to repeat, like ripples frozen into the spacing between clusters. Those ripples are called baryon acoustic oscillations, and they act as a ruler. When compared to the predictions of an unchanging dark energy, the ruler appears slightly warped, not broken, but stretched in ways that should not happen if the cosmic acceleration is truly constant. At first, the difference was too small to care about, but as the data sets grew, the discrepancy refused to go away. The largest surveys now show a consistent hint the acceleration might be slowing. If confirmed, this would be the first sign that the universe's dominant force is not eternal, but seasonal. In everyday language, imagine a balloon being inflated by a pump whose pressure is gradually dropping. At first, the rubber stretches faster and faster. Then, almost imperceptibly, the stretch begins to ease. The balloon still grows, but its skin no longer strains as fiercely as before. The air that once defined its shape is losing its vigor. Why does such a minute shift matter? Because cosmic time multiplies small differences into enormous consequences. If the push of dark energy is truly weakening, the future will not drift into infinite emptiness. Instead, expansion will reach a plateau, then slow, then reverse. The universe would not freeze. It would fold. Yet evidence is a fragile thing. How do we know we are not chasing statistical ghosts? The instruments are precise, but the cosmos is messy. Dust, lensing, and calibration can all mimic patterns that look like slowing. Still, each new data release reopens the same question. If the evidence keeps leaning in this direction, we must ask what could cause the slowdown. Some theorists propose that dark energy is not a constant at all but a field, like a thin mist spread through space. This mist could fluctuate with time, its pressure fading as the universe ages. If so, the epoch of rapid expansion we are living in might be just one chapter in a much longer cosmic cycle. Others argue that the observed drift is simply the universe revealing its deeper geometry, a subtle curvature we once ignored. The contradiction is both scientific and philosophical. We trusted a constant because it made the mathematics elegant, but the universe has never promised elegance. It promised truth, and truth is often irregular. If acceleration is fading, our equations must bend with it. To test this, astronomers watch how galaxies clump together over time. A universe driven by steady dark energy would prevent new structures from forming. Gravity would lose its race. But if the acceleration is slowing, clusters should continue to grow, merging like drops on a cold window pane. The more tightly galaxies bind, the weaker the outward pressure must be. So far, the clustering trend fits the rumor of change. Not proof, not yet, but enough to make the community uneasy. The once solid line of theory now trembles like heat over asphalt. Could the cosmos be entering a new phase without telling us outright? Could the very constant that defines the shape of space-time itself be fading? The chase for confirmation begins with instruments that see in wavelengths invisible to human eyes. Telescopes map redshifts, the stretching of light from galaxies racing away. These shifts act like fingerprints of expansion. By comparing them across distances and epochs, researchers can reconstruct the tempo of cosmic history. It is tedious, elegant detective work, translating color into motion, motion into fate. As new results accumulate, one unsettling picture forms. The cosmic push seems to have been stronger in the past than it is today. If that trend continues, the next billions of years may unfold under a slowly declining pressure. A gentle hand, once forcing galaxies apart, may someday loosen its grip. At its core, this is a lesson in humility. The universe is not obliged to maintain the parameters we find convenient. Every assumption about permanence is really a hope disguised as physics. We once thought the stars were fixed in crystal spheres. We once thought our own planet was the center. Now we are learning that even the grandest constants might evolve. The idea that acceleration is fading forces us to rethink what forever means. If expansion has a limit, then so does cosmic isolation. Galaxies that would have drifted beyond reach might someday be drawn back within sight. The horizon of knowable space could stop receding. In a distant future, the night sky might slowly brighten again as the expansion halts, an opposite of the cold fade we once feared. But the evidence is still young. The confidence bars are wide. No one yet dares to declare the death of eternal acceleration. The mystery remains open, its resolution waiting in deeper surveys and sharper instruments. Perhaps the next generation of telescopes will measure whether the universe's heart is truly slowing or merely beating in patterns we do not yet understand. And if it is slowing, what new physics lies behind that breath? We turn now to the strange idea that the engine of expansion might not be fading, but changing fuel entirely. A shift driven by an invisible field of actions and a hidden negative pressure waiting to take its place. Imagine that the universe breathes. Every rise in expansion could be an inhale, every slowdown an exhale. For billions of years, that breath has been deep and accelerating, space stretching faster with each cosmic moment. Yet if the push is fading, what if the breath is reaching the top of its arc? What if there is a limit to how far reality itself can expand before it begins to draw inward again? Among the many theories to explain this possibility, one stands apart for its audacity. It begins with a field, a kind of invisible ocean filling all of space, made of something that barely exists at all. Physicists call it the Axion field. Born from an attempt to solve a problem in particle physics, but now finding a second life in cosmology. If dark energy is not a fixed pressure but this ghost-like field, then it can change over time, rippling or decaying, its strength rising and falling like the tide. At first glance, the Axion is the most unlikely of saviors. It is unimaginably light, perhaps a trillion times lighter than an electron, so weakly interacting that it can pass through stars and planets without leaving a trace. Yet in the vastness of space, sheer numbers make up for weakness. Trillions upon trillions of these particles could fill every cubic meter of the cosmos, forming a background mist that exerts a gentle outward pressure. That pressure, in turn, drives the expansion of space itself. In the early universe, the Axion field might have been uniform, pushing outward steadily, indistinguishable from the cosmological constant we once assumed. Over time, however, the field can lose energy. Its waves flatten, its push slackens, and the energy density that once drove expansion begins to fall. When that happens, another term hidden in Einstein's equations starts to reveal itself, the cosmological constant, lambda, but not the positive one that repels. The negative form of lambda, if it exists, prefers contraction. This is the strange symmetry at the heart of the new models. A fading field leaves room for a latent negative term to dominate. The moment the two cross, the cosmic engine reverses. Space, once urged apart by a gentle outward pressure, starts to feel an inward pull. The equations that once described a universe racing toward emptiness begin to describe a universe preparing to fold. Simply put, the story that emerges is one of changing fuel. The cosmos that has been running on Axion pressure might be approaching the end of its supply. As that fuel thins, the hidden gravity of negative lambda takes over. The result is not a sudden collapse, but a long twilight of expansion, a gradual slowing spread across tens of billions of years. The galaxies keep drifting, but each year the drift is slightly less than the one before. The future is not a crash, but a hesitation. To visualize this, picture a stone thrown upward from the surface of a planet. At first it races away, slowing only imperceptibly. For a while, you might believe it will fly off forever, but gravity has patience. It waits, it balances, and eventually, even as the stone coasts outward, its motion begins to falter. Somewhere far above your head, it reaches a point of perfect pause, suspended between away and return. The universe, in this analogy, is the stone, and we are living in the moment when its speed still hides its destiny. If this model is correct, then the expansion of space will not continue forever. Over the next 20 or 30 billion years, the push will weaken until the balance tips. Beyond that point, contraction begins. Almost unnoticeably at first, the average distance between galaxies would start to shrink. After eons, the night sky would brighten as neighboring clusters edge closer again. Far in the future, background radiation would warm, stars would collide, and the cycle would move toward what cosmologists call a big crunch, a mirror to the Big Bang. Why should anyone take this seriously? Because the math supports it as cleanly as the eternal expansion scenario once did. In general relativity, nothing forbids a negative lambda. The sign simply changes the curvature of space. The same equations that describe an infinite outward flight also describe a finite arc if lambda turns negative. What changes is not the mathematics, but the narrative we prefer. Still, the evidence is far from decisive. The measurements that hint at slowing could also fit subtler adjustments in the nature of the Axion field. Some versions of the theory allow the field to oscillate, switching between periods of stronger and weaker pressure, producing a universe that breathes on timescales too vast for human senses. Others suggest that the field might couple with matter in ways we have not yet measured, creating feedback loops that alter its decay rate. In that case, the end may not be a single collapse, but a series of expansions and contractions, a cosmic heartbeat repeating forever. If such a cycle exists, then time itself may be circular. Each phase of expansion gives birth to new structures, which eventually dissolve into the next contraction, resetting conditions for another beginning. The universe could have no true start or finish, only an infinite succession of arcs, each with its own chemistry, physics, and perhaps its own civilizations rising and falling within. Every breath of the cosmos would be a generation. At its core, this idea reframes the question of purpose. If the universe is finite in age, but endless in renewal, meaning is not found in permanence, but in participation. Civilizations would not fight the inevitable collapse, but prepare to leave traces for the next cycle. Knowledge would be seed, not monument. In this way, even a doomed universe would remain alive with intention. But even this elegant picture comes with a shadow. Negative lambda implies that the vacuum energy of space is not only changing, but turning hostile. As the field decays, it releases its stored energy back into the fabric of space, accelerating the process of contraction. Once this tipping point passes, nothing can halt the slide. Stars will move closer, galaxies will merge, and the temperature of space will begin to climb again after trillions of years of cooling. Matter will unmake itself in heat and compression. The end will resemble the beginning. Human minds recoil at such scales. The numbers are too large, the times too slow. Yet every major telescope working today is, in essence, watching for this shift. Euclid and the Roman Space Telescope will map how the acceleration changes over time. If they detect a subtle curvature in the rate of expansion, that would be the first whisper of the transition from positive to negative dominance. It would mean we are already living inside the first phase of reversal. Why does this matter? Because the universe's fate is tied to the smallest particles imaginable. If the Axion exists, then the future of everything is a side effect of the faintest ripple in a field we cannot yet touch. It is a reminder that the grandest arcs of time depend on the tiniest scales of reality. When the field weakens, galaxies obey. When it fails, time itself rewrites the script. The scientists who model these possibilities do not speak of doom, but of balance. They see a cosmos that may one day end, yet in ending complete its own symmetry. For them, the question is not how to stop the reversal, but how to detect it, how to trace the fingerprints of a dying fuel on the sky. Every spectrum, every distance measurement, becomes a line in a long forensic poem written across the night. In everyday language, what this means is that the fate of the universe might depend on a leak in its energy tank. The cosmic engine has been running on a fluid so rarefied that only through its gravity do we sense it. Now, that tank could be slowly draining, revealing the deeper structure beneath. The outward drive fades. The hidden curvature reasserts itself, and the great expansion starts to slow its run. Somewhere in that long decline, civilizations may look up and see nothing unusual. The stars will seem stable, the galaxies unmoving, but in the arithmetic of space, the change will be written. The universe will be holding its breath between one infinity and the next. When it exhales, we will call it the beginning again. When evidence and imagination meet in this fragile balance, the chase moves to stranger ground, to the possibility that the universe's apparent acceleration is not about fading fuel at all, but about motion through a vast cosmic whirl where spin itself plays the part of force. A universe that spins sounds like a myth, something ancient poets would imagine, not a hypothesis modern telescopes might test. For centuries, scientists have treated space as impartial, without any preferred direction. The cosmic principle of uniformity, no up, no down, no center, has been one of physics' most sacred foundations. Yet every foundation trembles eventually, and a small group of researchers now ask an unsettling question: what if space itself has been rotating all along? To picture such a rotation, imagine standing inside a carousel so large that you cannot see its edge. If the rotation is slow enough, everything near you feels at rest. The air is calm. The lights appear still. Yet as the ride continues, you would begin to notice that forces seem slightly off. Objects lean without being pushed. Light curves in directions you cannot explain. The carousel's motion is hidden, not because it does not exist, but because you are moving with it. That, say some theorists, could be the story of our universe. This idea is not entirely new. A few cosmological models built after Einstein's equations were first written allow for global rotation. In those solutions, space itself carries angular momentum. The fabric of the cosmos drags along everything within it, bending light and time together in subtle spirals. The effect would be tiny, almost imperceptible, yet over billions of light years, it could leave fingerprints that careful measurements might find. The evidence, though ambiguous, is intriguing. Some surveys of galaxy spin directions report a faint asymmetry. More spirals twist one way than the other across vast regions of the sky. It is not enough to claim discovery, but it is enough to raise suspicion. If the bias is real, then it hints at a large-scale coherence, a background rotation that would violate the assumption of perfect isotropy. In plain terms, our universe might have a preferred orientation, like a coin that wobbles as it spins rather than turning perfectly flat. The galaxies, born from the same swirling conditions that shaped the early cosmos, could still carry that ancient motion in their rotation axes. Each cluster would then be a fossil of a greater spin, a record of inertia on a cosmic scale. If this subtle spin exists, it could change how we interpret acceleration itself. When space rotates, points within it experience inertial effects similar to what we call centrifugal force. The farther away a galaxy is from the cosmic axis, the faster it would appear to move outward. To an observer trapped within the whirl, that outward motion would look like a repulsive force, an expansion, but it would not require dark energy to sustain it. It would be a geometrical illusion born of rotation. This is the heart of the contradiction. We could be misreading motion as energy. What we interpret as the universe being pushed apart might instead be the side effect of living inside a spinning frame. The same effect that makes water bulge outward in a rotating bucket could be inflating our cosmic horizon. As the spin slows, the apparent acceleration would also fade, explaining why recent data hint at a possible decline. At first, such an idea sounds like heresy. The cosmic microwave background, the oldest light in existence, looks almost perfectly uniform. It should have revealed any global twist. Yet even there, anomalies linger. Tiny temperature variations trace patterns that some teams say could align with a rotation axis. The effect is smaller than our instruments can yet resolve confidently, but it leaves the door slightly open. What makes the spin hypothesis captivating is its restraint. It does not invent new particles or exotic fields. It only changes perspective, asking whether our cosmic frame of reference is truly still. The question is ancient, echoing the first time someone wondered whether the stars moved or we did. Once again, the answer might be that both are true, in different senses. To make this concrete, think of how you might detect the rotation of the Earth without ever seeing the sky. You could drop a pendulum and watch its plane of swing drift. The Foucault pendulum proves motion by reference to itself. In the same way, cosmologists look for large-scale correlations in galaxy orientation, in polarization, in the twisting of light from distant quasars. If the pattern aligns consistently, that would be the universe's pendulum nodding toward rotation. The implications are enormous. A rotating universe would break the cherished symmetry that underpins modern cosmology. There would be a true cosmic north and south, an axis defined not by stars but by space-time itself. The story of creation would acquire direction. a spin to history as well as to matter. It could even connect to quantum mechanics, where spin is one of the fundamental properties of particles. Perhaps, in some deep sense, the rotation of the universe is mirrored in the rotation of the smallest things. Why does this matter beyond pure curiosity? Because if rotation explains acceleration, then the cosmos may not be racing toward an icy void after all. The apparent push could subside naturally as the spin loses energy. Eventually, the outward motion would stall, leaving a universe that slows without invoking a changing dark energy or a collapse. It would be a quiet resolution to the puzzle, geometry balancing itself over infinite scales. Yet this model also carries an eerie echo. If space is rotating, it must have inherited that spin from something before the Big Bang. Rotation requires a pivot, and pivots demand time. A universe with spin therefore hints at a prehistory, perhaps a previous cycle of collapse and rebound. The cosmos could be the child of a turning parent, born from angular momentum passed down through eons of expansion and contraction. Human experience struggles to grasp such a lineage. On Earth, rotation is ordinary planets spin. Stars twirl, galaxies whirl. But to imagine the entirety of space-time doing the same is to step into a hall of mirrors, where every motion reflects a deeper one. We might be smaller participants in an infinite gyroscope, our destinies set not only by energy and mass, but by the angle of a cosmic wheel. Testing this hypothesis demands precision we are only now approaching. The Vera Rubin Observatory will soon catalog billions of galaxies, their spins and their alignments. The data will be a canvas vast enough to reveal whether there is indeed a preferred orientation to everything. If the distribution is random, the universe remains our neutral stage. If it is not, then we will have discovered the subtlest of all motions, the slow pirouette of creation itself. Think of it like this. We live inside a storm so large that we mistake stillness for truth. The stars are not receding because of an unseen fuel, but because we are caught in the eddies of a dance older than light. The realization would not end the search for dark energy, but it would transform it. Instead of chasing a vanishing pressure, we would be mapping the curves of a universal current. For now, the data stand at the edge of certainty. The spin remains a whisper in the noise, a rumor written in angles. Yet if future measurements confirm it, the story of cosmic acceleration will change again. The universe may not be fading or dying, only slowing in its turn, preparing for another rhythm in the grand motion of eternity. If the spin hypothesis proves false, then the fading of acceleration must have another cause, one that might reveal itself not in the structure of space, but in the choices of civilizations living within it. Every cosmic discovery is also a countdown. When we learn that the universe might slow, contract, or change course, we are not only talking about physics, we are talking about time limits for everything that can think, build, and dream within it. Expansion once promised infinite duration. A fading push or a future reversal rewrites that promise into a schedule. The question shifts from how long the universe will last to what any civilization can do inside its allotted window. Astronomers now work as timekeepers of the cosmos. They build machines that watch how galaxies move and how space itself curves. The Euclid telescope circles the sun, mapping billions of galaxies across 10 billion light-years. The Roman space telescope will follow, scanning supernovae to measure how brightness and distance change with redshift. Together, these instruments act like eyes watching the pulse of cosmic expansion, measuring whether that pulse is steady or starting to slow. On Earth, the Vera Rubin Observatory waits to join them, turning night after night into a continuous film of the changing sky. In plain terms, these observatories are the clocks of the future. By comparing the pace of expansion across time, they test whether the universe breathes evenly or hesitates. Every map, every light curve, is a frame in the story of the cosmos learning its own limits. The deeper we look, the more we realize that the limits are not just mathematical, they are practical. They define what any intelligent species can ever reach, see, or remember. If acceleration continues forever, galaxies will disappear beyond the horizon, their light stretched until no information from them can reach us again. Communication across intergalactic distances would become impossible. The universe would fragment into countless isolated islands, each adrift in its own darkness. If acceleration fades or reverses, the situation changes, but the pressure remains. Instead of isolation through expansion, there is the creeping return of density. The cosmic sea would begin to gather, pulling the islands closer. Either path limits opportunity, one through separation, the other through convergence. Why should that matter to us? Because every window for discovery and contact is temporary. Civilizations born in different epochs will face different skies. Early ones saw galaxies packed tightly together, easier to study, easier to travel between if they had the means. Late ones, like ours, live on the edge of visibility. Each passing billion years will erase another portion of the map. In that sense, the great cosmic survey we are conducting is not only science, but preservation. We are archiving the universe before it drifts beyond our reach. There is a quiet irony here. The more we learn about the structure of space and time, the more finite our options appear. Knowing that expansion might stop, or that contraction might come, gives us both warning and purpose. If time has a horizon, then the meaning of progress is to act before it arrives. The urgency is not panic, but focus, a recognition that understanding is a form of survival. Across human history, every leap in perception has followed the same pattern. We build tools to look farther, and what we see forces us to look inward. When Galileo lifted his telescope, the universe expanded from the planets to the stars. When Hubble measured redshift, it expanded again into billions of galaxies. Now, Euclid and Roman are expanding it once more, not in space, but in time. They are letting us see the rhythm of expansion itself. For the first time, we are observers of the tempo, not just the tune. If these missions confirm that dark energy is fading, the timeline of cosmic change becomes calculable. Physicists already estimate that a slowdown followed by a reversal could happen in roughly 30 billion years. That sounds infinite, yet it is less than 3 times the current age of the universe. Against that scale, our species is a flicker. Civilizations that rise now live in the early dusk of expansion, not the dawn. To them, the night sky is still rich, but it is dimming at the edges. So the question becomes, what do intelligent beings do with a limited sky? One answer is to move, to migrate outward while the horizon still allows it. The faster a civilization grows, the more distant light it can claim before isolation sets in. Another answer is to look inward, to encode its existence so deeply in the local fabric of matter and energy that the universe's later phases will still carry its signature. A civilization can try to last, or it can try to leave a trace. Both are forms of continuity in a cosmos that offers none by default. To put it another way, every act of observation is a moral act. Knowing that the future of space is shrinking forces a choice. Do we watch and record, building a history for whoever might come after? Or do we try to change our fate by altering the energy balance itself? The second path, manipulating cosmic expansion, borders on fiction, but it is no longer unthinkable. If dark energy is indeed a field, advanced beings might one day learn to amplify or dampen it locally, turning the flow of time into something more malleable. Even now, the concept of deadlines shapes scientific ambition. Euclid and Roman will operate for only a few years, yet the data they collect will guide theories for centuries. The Rubin Observatory will photograph the entire visible sky every few nights, turning transient events into an archive of impermanence. Each image is both a record and a farewell, a reminder that observation is the most human response to inevitability. There is another layer to the deadline. If contraction awaits, the density of the universe will eventually increase again. Radiation will rise. The cosmic microwave background, now a faint echo, will brighten as galaxies draw nearer and space compresses. For any civilization alive then, the stars will not fade. They will crowd together. New suns will ignite from collisions. Night will glow. But beneath that glow will be the slow tightening of time, the long approach of the final singularity. It will be a universe waking up as it falls asleep. How does one live knowing this? Perhaps the only honest answer is by treating knowledge itself as legacy. We may not alter the cosmic trajectory, but we can alter the meaning within it. Each discovery becomes a message in a bottle launched across epochs. The archives of today might be the myths of tomorrow, if there is a tomorrow to receive them. In the corridors of the data centers where cosmologists work, there is an unspoken sense of guardianship. The graphs and simulations on their screens are not just research tools. They are time capsules. When they map the faint light from a galaxy 10 billion light-years away, they are also mapping a civilization's chance to witness itself against the backdrop of forever. What they save now, others might not be able to recover. If the cosmic reversal ever comes, the first sign will not be visible in the stars. It will appear in the precision of equations, in the slow but steady bend of the expansion rate. Telescopes like Euclid and Roman will measure it decades before the night sky shows any difference. By the time the change becomes apparent to the eye, millennia will have passed, and the watchers will be long gone. But their numbers, their archives, will remain, silent witnesses left for successors who may face the same question again. At its core, this chapter is about motion, not only of galaxies but of meaning. The universe moves, and so must we, intellectually and physically. If acceleration is temporary, then curiosity is our way of staying in step with change. Each generation looks a little farther, learns a little more, and pushes the frontier of comprehension outward before the window narrows. In that sense, every act of learning is an act of defiance against entropy. When we stare into the future of space, we are also seeing the future of thought. The universe is teaching us to think in deadlines, to understand that knowledge must move faster than isolation, that understanding might be the one inheritance we can pass across cosmic time. The next cycle, the next civilization, will inherit a universe whose expansion rate carries traces of our measurement, our curiosity, our questions. Perhaps that is how existence remembers itself. We move now from the scientific to the existential, from observation to reflection, to ask what a finite cosmos means for consciousness itself, and whether the limits of space also define the limits of hope. When we look far enough, every map becomes a mirror. The universe we measure with equations and telescopes also measures us. It records our brief, bright attempts to understand what cannot be owned. The data that trace galaxies and dark energy are not just notes about the cosmos. They are reflections of our instinct to find meaning in motion. For centuries, the idea of infinity comforted us. It promised that time and space were so vast that our smallness did not matter. But if expansion fades, if the universe itself has a limit, then smallness acquires a sharper beauty. To exist at all inside a finite cosmos is to live in a singular moment between beginning and return. Eternity is not endless. It is cyclical, a circle we can touch only once. A universe that breathes, that spins, that changes its mind about expansion, is not a cold mechanism. It is a living geometry, constantly rewriting itself. We once thought that the end of time would be a tragedy, but perhaps it is a renewal we cannot yet imagine. If space can contract, then so can despair. Every collapse can be the seed of another dawn. Think of how light travels. A photon released from a distant star moves through billions of years without aging. To it, time does not flow. If the cosmos ever reverses, that same light might one day complete its loop, arriving again where it began. In that closed circle, creation and return are the same act. What we call endings might simply be continuity viewed from within. In everyday language, what this means is that impermanence is not failure. It is the pattern by which the universe keeps balance. Stars die to make new stars. Galaxies merge to create structure. Civilizations rise and fall, each leaving a trace in the same expanding and contracting sea. The story of the cosmos is not about survival, but about participation. Every moment of awareness adds a line to the larger equation of being. The real mystery is not whether the universe will end, but why it ever began. If the cosmos breathes, what breathes it? If it spins, what first turned it? And if it knows how to renew itself, can understanding that rhythm teach us how to live within it more wisely? We are made of the same ingredients that define the fate of everything. The dark energy we study may also be the background of our own consciousness, the quiet field that allows awareness to arise. Perhaps knowing the universe is the way the universe knows itself, through us, for a brief time. There is a quiet line that runs through all these theories. From Axion fields to cosmic spin to reversal, it says that nothing, not even expansion, is permanent. Yet within that impermanence lies the possibility of endless rediscovery. If everything repeats, then every thought, every act of compassion or curiosity will one day reappear, somewhere, in some form, under another sky. The universe does not ask for belief. It asks for attention, to watch, to measure, to wonder, is all ready to belong. Our maps may fade, our stars may die, but the act of asking remains part of the fabric itself. Awareness is the only thing that can outlast time, because it is what time makes possible. If the universe turns back on itself, what stories will it remember when the light comes home again?